What's up, y'all? Hello. Let me teach you math. Okay. So it's a longer section today, so I might skip some of the problems around. But it is 6.9. This says 6.8, but that should be 6.9. And it's improper integrals, and they're improper because they go from 1 to infinity. So what you're used to integrating, let me turn this over so I can get to the board. Okay, so you guys are used to integrating like area between two finite points. Like you're used to an equation like this, get the area between 1 and 4 or whatever, something like that. Now you're about to do like infinite areas, like from, I don't know, from 1 to infinity. Which is kind of, that would be exactly this integral right there that I just pointed at. So that's what's coming up, and the idea is the area ever finite? Like if I go from 1 to infinity, does the graph ever get close enough to the axis so that the area gets so small over time that it just adds up to a finite number? Or is it always infinity? But of course, if it was always infinity, then it wouldn't be a very interesting section, like I wouldn't be teaching it to you. So there are times where you get finite numbers. Okay, how do you do these? It's basically the same thing you're already used to. You just take the antiderivative, plug in the top number, plug in the bottom number, and subtract them, and that's your answer. Or at least that's what you're thinking informally. But formally, you can't plug in infinity. Like, you can't actually do that. So you replace the infinity with a finite number b, and you see what happens as the limit of b goes to infinity. Or more like you see what the limit of the function is as b goes to infinity. Okay, so here's what I mean. Let me make sure I don't want to say anything about that. Function is continuous. Yeah, okay. Let's just do an example. Oh, this is important for me to say because a lot of kids were confused last year about this. So converges and diverges. So if you take that infinite integral and you find that the result is you get an area of infinity, then that's what's called diverging. Infinite answer. Otherwise, you say converges, as in if I get a number out of my infinite integral, like I get 6 or something, then that's called converging. That integral converges. Finite answer. So any number. Cool. All right. So, all right. Let's get to the examples. Like I said, there are so many on here, and a lot of them take a long time, and they're tedious and annoying. So I might skip some of these depending, but I'll put up all the answers on Schoology. But look at this first one. It says, determine whether the improper integral converges or diverges. So, like I said, informally in your brain, you're just thinking, let me take the antiderivative of 1 over x, plug in infinity into the result, plug in 1 into the result, and subtract the 2. That's informally in your brain. But formally, like I said, you can't actually plug in infinity into a function. Like, that's not, you can't write that down on your paper. So what do you write instead? You write the following. You say, I can't actually plug in infinity, but I can plug in some number b and see what happens as that b goes to infinity. And that's it. That's the only thing that's different from in this section than in other sections. So, okay, now let me take the antiderivative. Antiderivative of 1 over x, hopefully you remember that that's, sorry, let me not forget my limit as b goes to infinity. So antiderivative of 1 over x, you remember hopefully that that's natural log of absolute value of x. And I'm plugging in, again, b and 1 and subtracting the 2. All right, so let me plug in b. That's the limit as b goes to infinity of natural log of, and then to make it just slightly less confusing, let me get rid of these absolute values because I'm plugging in a positive anyway. So like absolute value of a positive number like 7 is just going to be 7. So it makes no difference whether I keep the absolute value or not because these are all positive numbers. So let me get rid of the absolute value and say natural log of b minus natural log of 1. Okay, and then good news is that natural log of 1 is just 0, so it's just natural log of b minus 0. Again, that's because that part is 0. Okay, and then now I just have to figure out, okay, what's the limit as b goes to infinity of natural log of b? And this is why I said at the beginning of the year that it's important to know your parent functions, because this is very easy to do if you know your parent functions and very confusing if you don't. So what happens to natural log as b gets huge? If you keep taking huger and huger and huger numbers into natural log of b, what happens to the result? Well, if you know the parent function of natural log, that's going to look something like this. This is natural log of x. The graph of it looks like this. And so it kind of looks like it slows down at some point, and it does slow down, but it keeps growing forever and ever and ever and ever, and it goes off to infinity. So the limit as x or as b goes to infinity in this case is going to be infinity. So infinity minus 0 is infinity. Cool. So my answer is infinity, and so the answer to this question would be determine whether the improper integral converges or diverges. I got infinity, that means it diverges, like by definition. Diverging means you get an infinite answer. That was very confusing to kids last year, that word. Okay, very cool, nice. There's that one. So I got an infinite area. I think this next one, though, we get a finite area. All right, look at that. So, I should have said this on the last one, but I'll do it for this one, is it wants the integral from negative infinity to 0. In graphs, what does that look like? That means here's e to the x, again, good to know your parent function. Here's e to the x, and it wants me to find this area in light blue. What is that area from negative infinity up to 0? Cool, so you can see e to the x does get really, really close to the axis. So is that close enough that eventually it just like basically adds no area and you get some sort of finite answer for this? Let's figure that out. So again, in my brain, I'm just thinking take the antiderivative, plug in 0, plug in negative infinity, and subtract the 2. But formally on my paper, I can't plug in negative infinity. I have to change that negative infinity to a finite number and then take the limit as a goes to negative infinity. Sorry, my watch just said something, so I got distracted. But this is what I'm writing on my paper. There you go. And then I take the antiderivative of e to the x, plug in 0, plug in a, take this limit, I'm done. All right, antiderivative of e to the x would be, well, let me not forget this limit part. Antiderivative of e to the x, hopefully you remember, is e to the x. Plug in 0, plug in a. That would be limit as a goes to negative infinity of e to the 0 minus e to the a. Okay, e to the 0 is just 1. This is a negative right here that I'm highlighting. So 1 for this part, and then minus e to the a. So now I just need to know what is the limit as a goes to negative infinity of this function. So in other words, what is e to the a doing as a goes to negative infinity? Well, here's some good news. Look at this. Look at this. We had already graphed e to the x. And so what is that function doing as a goes to negative infinity? Look at this. Follow my red cursor, and you can see, oh, it's getting really, 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 really close to 0. In fact, if you plug in negative 3 trillion and do e to the negative 3 trillion into your calculator or whatever, you'll see that it's really, really small. Like your calculator is going to tell you it's basically 0, or it'll tell you it's like 1.3 to the negative 35th power. Like it'll tell you the answer maybe in scientific notation, but either way, this limit is 0. So this equals 1 minus 0, which is just 1. Cool, so there you go. We took an infinite area, or an infinite amount of space, and we got the area under it, and we ended up with a finite number, which is kind of interesting. And so to answer the question, determine whether it converges or diverges, I got a number, so that means converges. Again, that's just the definition. Nice. All right, so if you see infinities in your integral, that's what you're doing. If you don't see, well, let me make sure that that's the next example. Okay, this one is where both the lower limit and the upper limit is infinity. So it's the same thing. You just got to take the lower limit and the upper limit, and then change them out to a's and b's and take limits and stuff like that. So what this says is split it up into. Well, let's just do an example, and you'll see. So again, in my brain, there is no difference from the integrals I'm used to this. So I'm still just thinking, take the antiderivative, plug in infinity, plug in negative infinity. But like I've told you, formally you can't put that on your paper. So what do you do instead is you do this. You take the lower limit and replace it for an A, or whatever letter you like out of the alphabet. And then you're also going to have to take the limit of as b goes to something. So what you do is what this says right here is you split it halfway, or it doesn't really matter that it's exactly halfway, but that's sometimes the most convenient. So split it from going from a to 0, 4x cubed dx, and then from 0 to infinity, well, sure, yeah, we can just do it, this middle step. From 0 to infinity of that same integral. And so then that would look like limit as a goes to negative infinity of a to 0 4x cubed dx plus, and then again, I got to replace this infinity with a b. So plus the limit as b goes to positive infinity of this integral, 0 to b of 4x cubed dx. Okay, and then this part is a little bit confusing because if you think of the graph of 4x cubed, it looks like this that I'm drawing in red. Right there. And so the area that it wants us to get is all of this under the red function. That's all of this under the red function. And so you might think that this area is going to add up to 0 since it's symmetrical, and so this negative area here might cancel this positive area here. But what the rule actually says is that both of these parts have to converge. Otherwise, as long as one of them diverges, one of the integrals diverges, then we say the whole thing diverges, which is what's going to happen here. So watch this. Take the integral of the first part for now. That's going to be limit as a goes to negative infinity of a 0 4x cubed dx. I guess I didn't really need to write that again, but here's me taking the antiderivative. That would be limit as a goes to negative infinity of x to the fourth. Plug in 0, plug in a. That would give me limit as a goes to negative infinity of 0 to the fourth minus a to the fourth. And then what would this be? Well, that would be 0 minus, and then a huge negative number raised to the fourth power is going to become a huge positive number. So this will be positive infinity. And so because of that, I don't actually care what this side is. So this integral right here, I don't actually care what it is because I already know my purple integral diverged, so I don't even have to do this red one. I'm just going to say this integral diverges. But I'm hesitating because... I see it now. I'm hesitating because we got a positive out of here, but according to our graph, it should have been negative. But now I found the problem. It's because it should have been 0 minus that infinity. So this would have been negative infinity. But in either case, I still got an infinite answer, so it still diverges. Okay. Next one. Okay, so basically, the next few are just saying that an infinity doesn't have to be present for the area to be infinite. Like, for example, here, this integral right here that it's asking us to do next, it looks very innocent. 0 to 4 of this function looks like a normal integral. But be careful, because if I plug 0 into here, I get an asymptote, like I get 1 over 0. So what does this area look like? It would look like 1 over square root of x. It's like this function. And so you can see why it's an infinite and improper integral is because it goes from 0 to 4. Well, this is an infinite area right here that goes up forever. Okay, cool. So what do you do about that? You take a limit. Again, wherever the problem was, wherever the asymptote was, the discontinuity, you replace it with a different letter. So like what I mean is, I'm going to take this integral, but instead of the 0, which causes the problem, causes the asymptote, I'm going to do the limit as a goes to 0 of the integral from a to 4 of 1 over square root of x dx. And technically, look at the way I'm approaching this integral from the right side. So that's what this is saying, is take the limit as a approaches from the right. Okay, but everything else is exactly the same. If I'm going to take this integral, I actually like to rewrite it because I don't want to think that hard about what the antiderivative of 1 over the square root of x is. So let me rewrite this like x to the negative 1/2 dx. And then the antiderivative of that would be sorry, I'm putting this plus on the wrong side. It should be 0 from the right, 0 from the right, 0 from the right. Okay, but antiderivative of x to the negative 1/2 would be add 1 to the power. I get 1/2 out of that, and then divide by the new power. So divided by 1/2 is the same thing as multiplying by 2. Plug in 0, plug in a, and subtract. That would give me limit as a goes to 0 from the right of 2 times 0 minus 2 times, I'm sorry. I messed up. Because look at how up here originally, that was a 4, and then I changed it to a 0 up here for some reason. That's my mistake. I'm sorry. That should have been a 4, making this a 4, making this a 4. My bad. Okay, so 2 times 4 to the 1 half. Sorry, y'all. Minus 2 times a to the 1 half. And then see what happens as a approaches 0. Okay, so then this would be equal to, well, the limit is a goes to 0 of this, just 2 times 0. So this is going to be 0, and this will be 2 times 4 to the 1 half. So 2 times square root of 4 would be 2 times 2, which is 4. Wow, awesome. So does this integral converge or diverge? It's going to, well, I got a finite number, so it's going to converge. Nice. And then the other ones are basically the same thing. It's like, I think the next ones have you switch out both of the endpoints, or maybe now you switch the right endpoint or whatever, but it's the same thing that we were just doing. Like, look at this tangent one. Scroll up, there it is. This tangent one is just a right endpoint, this continuity. So if you don't remember what tangent looks like, it kind of looks like this. Negative pi over 2. This is pi over 2. And so it wants you to get this area in red. Boop, 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 boop. Is that infinite area going to be, is that going to converge or diverge? And so you would do the same thing I was just doing, but even the integral of tangent itself is annoying and it takes a long time. So just to not make this video too long, let me just post the answer key to this one and skip it, because this one is more complicated and more longer than it's worth the time for. But I think this ends up diverging. And to take the integral of that, by the way, of the integral of tangent, the antiderivative, you have to rewrite it as sine over cosine. And then you do u substitution with u being cosine. And du is negative sine. And then you go from there. You get some sort of natural log and you plug in numbers and stuff. But again, more trouble than I think it's worth. So I'll post the filled out notes for this. But the last one is a good one because this is how you'll normally see them, where it's kind of sneaky. So if you see this type of integral on the test, again, looks very innocent, looks totally good, but there's an asymptote in there. But I'm hesitating because I didn't make the answer key to this yet. I just quickly went over this, like just skimmed it. Oh, it's because it's halfway. Okay. Sorry. All right. So, again, like I said, this looks like a very innocent integral, but if you think about it, it has an asymptote right at the 1. Here's the 1. Okay, so this is going to look something like whoop going up, whoop going here, and it wants this area all the way to 2. Okay, so let's check if that converges or diverges. So notice you're going to have to split the integral from 0 to 1, and then get another integral from 1 to 2. That's what this is saying, is split it like that. So let's do it. That would be the integral from 0 to 1 of 1 over x minus 1 squared dx plus the integral from 1 to 2 of that same integral, or of that same function. Okay, and then change your problem so that you don't include the asymptotes in the integral. So that would be the limit as b approaches 1, 0 to b, and that b is approaching 1 in this integral from 0 to 1. That would be approaching it from the left side, boop, 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 that way. So this would be 1 from the left, and then plus the integral from a to 2, 1 over x minus 1 squared dx. And again, I'm just checking what's happening as a approaches 1, but this time from the right, that way. All right, and then like I said, if either one of those diverges, then I'm done with the whole thing, and I say the whole thing diverges. But if both of them converge, then I add them together, and that's what it is. So let's check. I'm going to do this one. I want to take the antiderivative of 1 over x minus 1 squared. I frown because I don't know the antiderivative of that, so I got to do u substitution, because if I make u be u equals x minus 1, then du equals 1 dx. So now this integral turns into actually, let me do it off to the side, because I don't want to change my limits of integration. So my antiderivative, just do this off to the side, and then I'll go back to the original problem. This is going to turn into 1 over u squared du, meaning my antiderivative is going to be 1, well, I don't know yet. This will be u to the -2nd du. Now I can take the antiderivative of this, add 1 to the power, divide by the new power. That gives me -1 over u. But u originally was x minus 1, so there it is. That's my antiderivative, and now I'm just going to put that result over here. 1 over x minus 1, evaluated at b and evaluated at, what was it, 0. Okay, plus the integral on this side, but I'll do that later. So plug in b into this, and I'm going to get limit as b goes to 1 from the left, 1 over b minus 1 minus 1 over 0 minus 1. So this second term right here that I'm circling, no problems with that. But what is the limit of this first term right here? I think that's going to be infinity, because if I approach 1 from the left, I'm going to get 1 over 0, or really close to 1 over 0. When I'm approaching 1 from the left, like if I plug in the 0.9, I get 1 over 0.9 minus 1. That's going to go to -1 over a negative really small number, so this would go to negative infinity, meaning this whole thing is going to diverge. All right, hopefully that makes some sense. Again, I'm not even checking this one that I'm circling right here, because already my first one diverged, so the whole thing's going to diverge. All right, come to me if you have questions. I know this was a longer video, and I made some mistakes here and there, so sorry about that. Come to me with questions if you have them, but I will say that most of the time you'll see integrals that are very obviously improper, like they'll have the infinity in there, or I've seen these on the AP test where they say evaluate the improper integral, like it says it even in the question, so you don't have to wonder, or it'll be a multiple choice question that says evaluate the integral, and one of your answers is it diverges. So it's like a good hint that, like, oh shoot, I should check if this is an improper integral, in case it's one of these like sneaky ones where it's not obvious that it's improper until you realize that there's an asymptote in there somewhere. All right, now I'm done for real. Good job to you all. Good luck, and come to me if you have questions.